Welcome to this video on chemical kinetics, presented by Dr. Luis Bello. Chemical kinetics is the study of reaction rates and mechanisms. The reaction rate is the change in concentration over time. This field is important in many areas, and key factors include the nature of reactants, concentration, temperature, and catalysts. Reaction rate can be expressed as the negative change in reactant concentration or the positive change in product concentration over time. Units are typically ems per second. We differentiate between average and instantaneous rates, noting that the rate generally decreases as the reaction proceeds. Several factors affect reaction rates: the nature and physical state of the reactants, their concentration, the temperature, the presence of a catalyst, and for heterogeneous reactions, the surface area. Higher reactant concentration usually increases the reaction rate due to more frequent collisions. However, this relationship isn't always linear and depends on the specific reaction and its rate law. Temperature significantly affects reaction rate. The Arrhenius equation describes the relationship between the rate constant, K, and temperature, T. It includes the pre-exponential factor, A, the activation energy, EA, and the gas constant, R. Key insights from the Arrhenius equation include: reactions with lower activation energy proceed faster, increasing temperature increases the rate constant, and the relationship is exponential with respect to temperature and activation energy. Rate laws express the reaction rate in terms of reactant concentrations. The general form is rate equals K times the concentration of A raised to M and the concentration of B raised to N. The exponents M and N are the reaction orders, determined experimentally. The overall reaction order is the sum of the exponents in the rate law. We define zero order, first order, and second order reactions based on these exponents and show their respective rate law equations. Key points on rate laws include: the units of the rate constant depend on the reaction order, the rate law reflects the rate determining step, and rate laws are determined experimentally using initial or integrated rate laws. For the reaction of two NO molecules with one O2 molecule, the rate law may be second order in NO and first order in O2. For a zero-order reaction, such as a catalytic decomposition, the rate is simply equal to the rate constant. Consider the reaction between NO and O2 to form NO2. Step 1 is to write the general form of the rate law, where the rate depends on the concentrations of NO and O2 raised to their respective reaction orders, M and N. Integrated rate laws describe how reactant concentration changes over time. They are derived from the differential rate law and are useful for determining the reaction order and calculating concentrations at any given time. For zero-order reactions, the rate is constant. The integrated rate law is concentration of A at time t equals initial concentration of A minus K times t. A plot of concentration versus time yields a straight line. For first-order reactions, the rate depends linearly on the concentration of the reactant. The integrated rate law is the natural log of concentration A at time t equals the natural log of initial concentration A minus K times t. A plot of the natural log of concentration versus time is a straight line. Here's a problem. A first-order reaction with reactant A has a rate constant of 0.693 per second and an initial concentration of 0.100 m. We need to find the concentration of A after 2 seconds and the time for A to decrease to 0.025 m. Step 1 is to write the integrated rate law for a first-order reaction. We have the natural log of A at time t equals the natural log of initial A minus K times t. We can rearrange this formula to solve for concentration or time. To find the concentration of A after 2 seconds, we substitute the known values into the integrated rate law and perform the calculations. The final concentration of A after 2 seconds is 0.025 m. To find the time required for the concentration to decrease to 0.025 m, we rearrange the integrated rate law to solve for t. Substituting the known values and calculating shows that it takes 2.0 seconds. The final answers are: after 2 seconds, the concentration of A is 0.025 m. It takes 2.0 seconds for the concentration of A to decrease to 0.025 m. This slide is a placeholder for the integrated rate law for second-order reactions. It shows the relationship between concentration and time for this reaction order. This slide serves as a visual break within the discussion of integrated rate laws and reaction orders. The half-life of a reaction, T1/2, is the time required for a reactant's concentration to decrease to half of its initial value. It is a key characteristic used to measure reaction rates. This slide would typically contain the half-life expressions for zero-order reactions, showing its dependence on initial concentration. This slide would detail the half-life equation for first-order reactions, which is independent of the initial concentration. This slide would cover the half-life formula for second-order reactions, which shows an inverse dependence on the initial concentration. This slide serves as a simple visual divider before moving to the next major topic. Collision theory explains chemical reactions. Effective collisions require molecules to collide with sufficient activation energy and the proper orientation. Activation energy is the minimum energy required for the reaction to occur. Reaction mechanisms are the step-by-step sequences of elementary reactions. They may involve intermediates, which are formed and consumed during the process. The rate-determining step is the slowest step, controlling the overall reaction rate. Elementary steps are classified by molecularity. Unimolecular involves one molecule, bimolecular involves two colliding molecules, and termolecular involves three colliding molecules, which is rare. Catalysis involves a substance, the catalyst, that speeds up a reaction without being consumed by lowering the activation energy. Catalysts can be homogeneous, heterogeneous, or biological, such as enzymes.